Okay. Okay. All right. So today, lecture on the 5th lab. So I know we're already pretty far, huh? On the 5th lab already. So that's going to be for the Charpy Impact test. But before we get started on that, your grades for Memo 2 and Memo 3 now. I'm sorry, don't have them. I think I said before, I always like to, usually get your grades in within a week from when you submit your memo. Just been really busy lately, so haven't been able to get them in yet. I've been working on my own midterm project that's due today, like this whole week. So that's why I don't have your Memo 2 grades yet, but you'll have them in for sure before your 4th memo is due, which is next Friday. So yeah, I'll have them graded before then for sure. But of course, make sure you take a look at all the feedback from Memo 1. That'll be the most detailed memo for all the feedback that I have. Okay, so before we actually get started on the lecture, I want to show you a little video for what the Charpy Impact is going to look like. So, in the lab, you've probably kind of seen these two setups. So we have two of these in the lab. They look, a bit different than this one. But, so what we have here, we have a pendulum, and then there's going to be a little notched specimen that's kind of in the center here, like down here. And we're going to load up this pendulum. We don't have a little wheel here. We actually have to lift it up ourselves. And I think it's like 60 pounds. So if only one person is doing it, make sure you're using good form, right? Because don't want to throw out your back. But we got to load it up, and it'll kind of lock into place at the very top. And then you can release it when you're ready to do the test. All right, so we load it up. And again, there's a little specimen down here that's notched in, and that's what you're going to fracture. So it looks something like this, and you're going to line it up on this test bed here and try to get it as centered as possible. This guy, he has like a little, I don't know if he shows it in the beginning or not. This person, they have something to actually line it up in the center. We don't. Let's go back here. All right, so, there it is there, and then the pendulum is going to strike it, and then it's going to break. And this little dial gauge here in the front, this is going to tell us the amount of energy that is absorbed on impact. So that's what we're going to be reading throughout the entire test. For us, the units are in foot-pounds. Here, they're using joules. And so, that one right there, let's see, let's go back a little bit. They were at around 90 joules. That's what it looks like here. Or actually, no, 30, I think, because it's in red. I don't know. Either way, if we look at this fracture appearance, it's really ductile, and we're going to be talking about that a lot today. The fracture mode. So this fracture appearance here, you see that it's kind of torn apart. It's very jagged, very rough, and it's not actually even fractured into two different pieces. So this is going to be a ductile fracture mode. Right, and here's a different test, different specimen. Let's see what this one looks like. So you see this one, it hardly absorbed any energy for this one. So this fracture appearance should look very clean, a very clean cut, and it should be separated into two. They show both of them at the end, I think. Okay, there we go. So you see this one compared to the last one, it's actually broken into two, and again, it's very clean cut. So this is a brittle fracture mode. And I think they might compare both of them at the same time. At the end, side by side. There you go. Okay, so we're going to be taking pictures actually after we do these tests in the lab. At least that's what we've done before. So we have like a kind of like a macro camera, and we'll take pictures of the fracture surface after each test, and then you'll talk about that in your report. Okay, so on the left, ductile fracture mode. On the right, a brittle fracture mode. Okay, so that's what it looks like. All right, so then we'll start the notes. That was my project. Okay. All right, so notes for the Charpy Impact. It's going to be a pretty quick lecture, to be honest. It's fairly simple for what we're going to be talking about today. So definitely not as long as the column lab report. Oh, and since we were talking about that now, the data reduction for the column, hopefully that's going well so far. I think for this section, you guys have all of the data. I think everyone's uploaded that to Discord, and I have all of that on Canvas. And, remember for two of the test setups, you guys, in the very beginning for pin and fixed pin, I think for a few runs for each of those groups, we didn't have the pin support for a few of them. Wasn't in the procedure, so, I didn't catch it too. But because of that, those first few runs, again for pin and fixed pin, they're going to be a little wonky. Well, theoretically, they should be a little bit wonky. So definitely talk about that in the report. And I think for other test runs too, if there is, an issue with the rod or something, most people, they left a comment on their Excel sheet. So, definitely take a look at that too. So I know like occasionally like a rod was already like bent a little bit before a test, and that affected the amount of load that it could take. So that's another source of error. So just look at all that stuff before you write the report. And yeah, I've seen some of the graphs from some students already, and I think for this section, they're not great, to be honest. That's not a knock on you guys necessarily. In the beginning without having the pin support, that's a big one there. But even besides that, some of the data points are it's a pretty big gap compared to the theoretical values. So again, refer to the Excel sheets if there was like a bent rod before it started, or a big one is the fixed supports being bent. That's going to change things too. So you're going to really need to think about the sources of error for this experiment when you write your report. Someone brought up, I am not requiring a percent error calculation for this report. You would need that. If I did, that would be for 12 data points, right? So what I would personally recommend is if you have a very large discrepancy between the actual and the theoretical values, maybe to support your memo a bit better, you can actually calculate that percent error, and that's part of your discussion that way. But I'm not actually requiring the 12 calculations for percent error. But again, to supplement your report, you might want it for some things. Okay, let's get started though. Yes, Charpy Impact. So far in the past experiments that we've had, especially for the first, second, I guess all of them really. For all of our experiments so far, we've been using the software to actually prescribe the amount of deformation per minute that we have. So that's set in the software by test speed, I think it's called in there. And typically we set it at 0.01 inches per minute. So that's really slow. Last week, I think we set it to 0.02 to make it go by a bit faster. And but either way, that's still really slow, and that's something that we prescribed, right? We told the machine to apply the deformation at a constant rate. And then for this experiment, it's gonna be very different because it's not gonna be really slow like that. It's not gonna, this failure is not gonna occur over the course of minutes. It's gonna be, instantaneous. It's an impact test that we're doing this time. So the strain rate, instead of being really slow, is going to be very, very fast. So I guess that's the biggest difference in this experiment versus the past. Okay. And again, from this strain rate, what that's really telling us, maybe I shouldn't phrase it that way, but when we have that high strain rate, it's high because of that impact that we have. So it's kind of this instantaneous load. And from that, the dial gauge that's on the front, once the pendulum, when the hammer hits the specimen and the specimen breaks, that's going to tell us how much energy that the specimen was able to absorb. So, for us, we're not using SI units, we're using English, so we're using units of foot-pound. Okay, and then this amount of energy that is absorbed on impact, that's going to be the impact toughness of that material. So, that's a good thing to know, that it's a toughness, not something like, strength. But that's just, we're not going to focus on that too much in this experiment. The actual, I guess, definition of toughness, but definitely good to know. And you can actually calculate toughness too from a stress strain curve. So, we've had the stress strain curve in the past for different tests, like for the tensile test. And for that, we have our graph here, where we have strain, and then we have stress. To calculate the toughness for the, each material, you're going to have your stress strain curve, and then you can calculate the toughness by calculating the area under the curve. So again, we're not doing a tension test or anything like that to have a stress strain curve in this experiment. But, in the past, we could have calculated toughness if we wanted by calculating that area under the curve. All right, so if we have these three different materials, the one in blue, you can see that it's very strong. It can handle quite a lot of stress, but it doesn't go under a lot of strain, so it doesn't deform very much. So if you're going to calculate that area under the curve, it's not too high, so it's not very tough. And same thing with the red material. It's really weak, but it can deform quite a lot, so maybe something like rubber. So again, though, that's not very tough. That area under the curve is pretty small. But then if you calculate the area under the curve for the green material, that might be something like steel or a material similar to that. It's pretty strong and it can deform a good amount too. And so that's going to have a much larger area under the curve. So that material, at least relative to the other two, that one's going to be the most tough in this case. So again, something to, just keep in mind. I'm sure you probably have like questions like this in your actual stress mechanics class at some point. But for us, we're not calculating toughness this way because it's an impact test. We're going to get that toughness. We're going to get the amount of energy absorbed on impact directly, just right away from that dial gauge on the test setup. All right. So next thing is, I guess, a little, refresher on a brittle material versus ductile. So we just know in our everyday life what's a brittle material versus ductile. So for brittle, you might have something like ceramics or like glass. It's strong, but when it fractures, it's gonna break in very clean cuts. So they're not gonna deform very much at all. So when you drop your phone and you break the glass, it sucks. Usually it's pretty strong, but once it breaks, it's gonna just shatter and have a clean cut. And if you compare that to a ductile material, again, I think I said rubber earlier, but for those materials, they're gonna deform quite a lot before they break. So a very extreme example would be like gum. You can stretch it quite a lot, so it's deforming a lot, and then it's finally going to break at some point. But those aren't going to be as strong as their brittle counterparts. So we know that in like everyday life, for those materials, but in this lab, we really want to focus on not that kind of everyday kind of life differentiation for that, but we want to focus on the fracture mode. So that's different. We're going to say, how does a material behave when it fractures? So you can have a brittle fracture mode or a ductile fracture mode. And in this test, for some materials, they're going to behave differently at different temperatures. So we'll draw some graphs for that in a second here. But again, we don't want to kind of box ourselves into what's a brittle material versus ductile, because that's kind of vague. In this lab, it's going to depend on the temperature that they're subjected to. Okay, so this part might seem a little bit repetitive, but just keep in mind that it's a fracture mode and not just talking about the material by itself. So ductile fracture mode, it's going to deform and then fracture. And then, of course, for a brittle fracture mode, it's going to have very little deformation when it fractures. Okay, so now for, I guess, kind of a morbid example, and I got this from Dr. James a few years ago, and I don't know, there's a lot of good examples like this, but for a good example for differences in how material behaves depending on the temperature would be the Titanic, right? So I guess it was made out of steel, So when steel is hot, it's going to behave in a kind of in a ductile manner, so it can deform quite, maybe, relative to other materials, it can deform quite a lot. So it has a ductile fracture mode when it's in warm or hot temperatures. But as the temperatures get really, really cold and you're in cold water and you hit an iceberg, at that point, that steel is going to behave in a brittle manner. So it's not going to be able to deform very much. So there's very little deformation, and then it's going to fracture. I think there's actually a different example too. There's some, I don't know, like naval ship or something before. I forget what it was called, but there was some big like warship or something. It was in cold water. It was made of steel, and it actually split into two. I think just without even hitting anything. Let's see if I can find it. Warship split in two steel. I don't know. Let's just see if we see it. Yeah, here we go. So you can kind of look this up here. Okay, got a site that was made in the, I don't know, 80s. So you see this is split here. And yeah, so unexpectedly cracked in half for no apparent reason while I was at the dock. But again, that was because this water was so cold, and this was made of steel. I'm pretty sure this is the same ship that I'm thinking about. Okay, so that's just a real life example. Oh, okay. Yeah, I don't know if it was Japanese or American. So yeah, good example though of how the material, it can, depending on the material, it can behave differently depending on the temperature. So we're going to see that in this lab with steel. I think we, just like usual, we have aluminum 60, 61T6, and I think we're all using the same steels as usual too, 1018 and 1045. So I'll add in a little something right here. An example, steel. And the Titanic. Okay, so next thing we're going to talk about is what's called the ductile to brittle transition temperature, or DBTT. So now we're actually going to have a graph here, and we're going to see for some materials when there's a transition from going from a ductile fracture mode to a brittle fracture mode. Okay, so first I'll define it, and I don't know, to me when I first heard it, it seemed, I don't know, like there's a lot going on, but we're gonna have a little graph and then I think it'll make a bit more sense. So this ductile to brittle transition temperature, the definition is when this is the temperature for when our impact energy is halfway between the impact energy for the highest temperature and the impact energy for the lowest temperature. Okay, so I'll write it out, then we'll actually get a better understanding when we have a graph. Okay, so I don't know, maybe I'm dumb, but when I first read this, years ago, it was what? So again, it's the temperature when the impact temperature, or impact energy rather, is halfway between the impact energy of the highest temperature and the impact energy for the lowest temperature. So this graph here, this is kind of representative of, we'll see later, but what is it? A body-centered cubic material. So that'll be something like steel. And on the x-axis, we have temperature. And on the y-axis, that's the energy absorbed on impact. Okay. And of course, our graph isn't actually going to have this implied sample size. Once we actually make this graph, we're going to have our little data markers throughout here. So, we'll have 6 of those, so not very much. So we have 6 different temperature kind of environments that we're going to be looking at. But anyway, so let's pretend we have this graph here, and let's say it's for steel or whatever material, doesn't really matter. But you can see that there's a transition from going to ductile to brittle. So we're going from the right to the left here, which is kind of weird. But on the right hand side of this graph, and this region here, we have a ductile fracture mode, because this material, it's absorbing quite a lot of energy on fracture. Okay, and then as we continue to go from right to left, it's going to absorb less and less energy on impact, and at the very low end here, it's behaving in a brittle fracture. Its fracture mode is brittle down here, so we're at these really cold temperatures and it can't absorb very much energy on impact. So again, that would be something like steel. So we talked about that ship. That wasn't, an impact scenario there, but either way, it wasn't able to have a ductile fracture mode at that low temperature. But for us, for this lab, we're looking at that impact. So these materials, again, I think it's body-centered cubic, they aren't going to be able to absorb very much energy at all on impact in these very cold environments. Okay, and I'll give you all of the temperature kind of environments that we're going to use too later on. So let's do some labels here. So in this region, it's a brittle fracture mode. And up top here, we got a ductile fracture mode. Okay, and then somewhere in the middle, we're actually transitioning from ductile to brittle. So most materials, they aren't going to have as drastic of a curve here. Here it's a very well-defined curve from when we're transitioning from ductile to brittle. This is, again, exaggerated. Most materials like this aren't going to be as drastic. Okay, but there's one point that we can find, actually kind of calculate, and that's going to be our ductile to brittle transition temperature. So what we're going to do, we're going to look at the impact energy that is absorbed for the highest temperature. So that's right there. And then look at the impact energy absorbed for the lowest temperature. It's down here. Then we'll get the average for that. So when it's halfway in between the highest and the lowest impact energy, just, I don't know, green. Okay, it's maybe right there. We can draw our horizontal line. We'll get this point here, and then we can just go right on down. And then we can get our temperature, and that temperature right there, that'll be the ductile to brittle transition temperature. All right, so we're going to be looking at that for part of the data reduction that we do for this lab. Now, for something that's like aluminum, so I'm going to make another graph soon here for 3 different kind of materials. For aluminum, it's not going to have this drastic curve at all. In fact, it's going to behave pretty much the same throughout this range of temperature. So in that case, it's kind of silly to say when you have a ductile to brittle transition temperature, because for aluminum, it's going to be behaving ductile pretty much the entire time. But again, we're going to have that graph in a second. Okay, and then just some notes here, I guess just for your own kind of use or reference. You know, usually we want to have our ductile to brittle transition temperature to be very low. You know, because usually we're not going to be in an environment, unless you're in like Antarctica or something, where you're going to be working in really, really cold conditions. And if you are working in those conditions, then of course you're going to have to find a material where it's suitable for those conditions. But you know, for typical like everyday use, we're not in these very cold environments, so we want to have our transition temperature to be very low. And that way, our material is only going to fracture more easily at those very low temperatures. Okay, and then of course that's also implying that we want to actually be, you know, when we're in use for whatever application we have, we want to be above that transition temperature so it doesn't break. Okay, so now let's talk about material structure. So I've kind of had a few hints on that already throughout the lecture here. So the material that we just drew on this graph, I said that was a body-centered cubic structure. So some of you actually might be taking this class. I don't know if it's offered this semester, but there's a class on campus for material structures, and I've never taken it, so I don't know too much about it really at all, to be completely honest, but I know I've had students in the past that have taken this class, so if you've taken it, then you probably know, well, you for sure know more than me on this part. So this won't be anything that we need to actually talk about in the lab report. We're just going to be looking at our 3 materials, aluminum and the 2 different steels. But this is good for just background knowledge on the kind of curves that you can expect to see for this this graph here for energy absorbed for different temperatures. Okay, so we're going to have the curve that we just had. So this will be for materials kind of like steel. And these ones, as I said, these are body-centered cubic structures. So we're going to give that a little acronym of BCC. So body-centered cubic, I'll write that below to you. And then an example for this would be something like steel. All right, and then we're going to have another kind of variety in our experiment, which will have a curve like this. So much different, right? And these are called face-centered cubic structures. And an example for that would be something like copper or aluminum. All right, and you can see there for the range of temperatures for an FCC material, it's not changing very much at all. In fact, the curve that I drew here, it's kind of exaggerated too, just to kind of emphasize, or to kind of just dramatize it, I guess, a little bit. So both of these curves are exaggerated, but you're going to see that general trend in the lab. So for this FCC material, the energy absorbed, it should be fairly constant in our lab. And there's other things going on there where it might affect that. But, once we're in the lab, and we'll talk about it then too, but you want to make sure that when you take it from whatever temperature environment that it's in, that you get it on the test stand and you run the test as fast, but of course as safe as you can. But this is what we should see in the lab. So we should see our steel materials, they're going to look something like this curve. Again, not as dramatic, most likely. And then our aluminum material, it's going to look something like this. So you'll see it should be pretty constant for aluminum. So it's going to behave as, it's going to have a ductile fracture mode for this entire range of temperatures. So it's always going to absorb a good amount of energy on impact. And when you look at it after it's failed, just like you saw in the video, it's going to be bent. It's probably not even going to be broken into two because it's absorbed so much energy. So it's going to look like a very rough and jagged appearance. Okay, and then for steel, you're going to see that mostly for these low temperatures, you're going to see that it's going to be a clean cut. And again, that's because it's a brittle fracture mode down here. It can't absorb very much material or very much energy at all on impact. But as we increase the temperature for steel, then it can absorb quite a lot of energy on impact. And it's going to be a ductile fracture mode, so you'll see that is pretty jagged. And then right around our transition temperature, we're going to have a mix of the two. So it might be a little bit smooth or a little bit of a clean cut, but it's going to be a little bit kind of rough too. It's going to be a combo. Kind of like our intermediate rods for the column. We said that was a combination of crushing and stability failure. So it's kind of in between there. So same kind of thing here. Right around the transition temperature, it's going to be a combination of both a brittle fracture mode and a ductile fracture mode. Okay, and there is one more curve that we have here, but we're not going to see it in our lab, but I'll draw it just for your own reference. Okay, so down here we have high strength alloys, and again, we're not going to see this for this experiment, but that's what we have. So, remember that this graph, it's energy absorbed or toughness compared to temperature. So, back to our stress strain curve that we made up here, even though this isn't a graph for an impact test, it's a stress strain curve, so something like when we have a tensile test. We have this really strong material here, but it's not tough at all. So I think like ceramics, right? They're very strong, but they are not tough at all. And again, we can calculate that directly from the area under the curve. So same thing down here in this graph. You have the high strength alloys, and they're down here, but that's again because they're not very tough. All right, and then again, FCC, that's face-centered cubic. Guess I'll just write that here. Face-centered cubic, and that's referring to the kind of the crystalline structure of the material itself. And then BCC is body-centered cubic. Okay, and then the 6 different temperature environments that we're going to have for this lab, let me go to it. We have liquid nitrogen to dry ice to water ice, so just ice and water, and room temperature, and then boiling water, and then an oven. Okay, so we have those 6 different environments. Okay, so maybe we got our 6 data points, something like that, right? So a little recap on what we're doing in the lab. Let's pretend we're just looking at this steel one here. We're gonna test steel, so we're gonna have it in a liquid nitrogen environment. So the lab technician Don, he'll help out with that part because he's certified to handle that. And then you all still actually put it in on the test bed, and for liquid nitrogen especially. So the low end and the high end for the temperature, you got to be quick when you test it because you don't want to leave this out for liquid nitrogen. You don't want it to just stand there on the test bed for a while because it's starting to warm up. So you got to be quick, but you got to be safe too for this lab for sure. So anyways, again, we're starting at liquid nitrogen. We're going all the way up to an oven temperature environment. And we're going to drop the pendulum or the hammer onto that. I keep getting something in my eye. We're going to drop that right onto the test specimen. It's going to fracture. You're going to look at the dial gauge on the front, and that's going to directly tell you how much energy was absorbed on impact, and that's in units of foot-pounds. And you're going to jot that down, so probably make an Excel sheet again, I think would be the best thing. And you're going to be doing that for our 3 different materials, so aluminum, and we have 2 different steels. And of course, I'll give you the exact model of aluminum and steel in the lab. Pretty sure it's the same as we've always had, but I could be wrong there. I can't remember off the top of my head. Okay, so for the steels, we're gonna get a graph that looks something like this when we make our plot for energy absorbed versus temperature. And then for aluminum, we're gonna get a graph that looks like this. So aluminum should be pretty ductile for its fracture mode the whole time. And then we're gonna calculate the ductile to brittle transition temperature. It really only makes sense for something that is going from ductile to brittle or brittle to ductile, however you want to think about it. Okay, so we're going to be doing that, and you're going to obviously discuss that in your report. And that's going to be it for this lab. So I think this lab is actually probably the most fun one, or most interactive at least, because you're not just pressing play and doing nothing the whole time. You're very, very involved with this lab. So I think it's a good one. All right, so and also a reminder, your grades for Memo 2 and Memo 3, I'm going to get started grading those tomorrow. So Memo 2 for sure will be graded before Memo 4 is due. Memo 4 is due next Friday. So you can see that on Canvas too. All right, so any questions on this lecture from today? Nope. All right, so that's all I got planned for today. So there's no questions. You guys are free to go. Have a good weekend, and good luck with all the midterms or projects or whatever you got going on right now.
Thank you. Have a good weekend, Professor.
Thanks. You too.
Thank you, Patrick. Have a good one.
Thank you. You too. Oh yeah, Halloween. That's coming up, huh? Yeah, you too. Ryan, you got a question? All right. All right, I'm gonna end it.